Oh, wait a second. This is visible, right? Yes or no? Yes, guys?
Yes, sir.
Yes, sir.
Okay, fine. So in the last lecture, the main idea that we ended up was with the delta U is equal to Q plus W, where Q represents the heat and W it represents the work, right? And we said that heat can be positive and negative. Heat can be positive, and the value, I mean, the sign conventions, if you're talking about sign conventions, that means heat we can take as positive and negative. We will take positive when heat is given to the system, right? Heat is given to system. And if heat is taken out of system, then it is going to be negative. Similarly, for work also, we said that there are two conventions for sign, again, positive and negative. So if work is done on the system, work is done on the system, then we will take that work, whatever amount of work is done in the units of energy, that we will take that as positive. Okay, we will take that as positive work. Positive in the sense that, for example, if I do 120 joule of work now, that means I will have plus 120. Now, if the system was doing a work done by the system, then we will take that work as negative. That means if the system is doing, let us suppose 120 joules of work, that means that will be minus 120 from the internal energy, Okay. So I hope all of this is clear to you guys. Yes or no? About the sign conventions?
Yes, sir.
Yes.
Right. So this is the system. If anything is given to the system, it will be negative. Either heat is given to the system or work is done on the system. And if heat is given out of the system, if heat is given or work is done, that will be positive. If heat is given out or work is done by the system, if anything goes out, it will be negative. Okay. So you may keep this picture in your head. If it comes inside the system, that means it is positive. And if it is going away from the system, that means it is going to be negative. It is going to be negative. So from that, you can write this question. And I hope you have your pen and notebooks. Okay, you have to have your pen and notebooks. I will give you some questions, but you don't have to write notes. Okay, but you need to do some questions. So please write this question. How are you, Khalil, Abdurrahman? How are you guys? Yes, am I audible to you, Khalil and Abdurrahman?
Yes, sir.
Okay. I hope all of you have written the notes. Yes or no? From the previous class?
Yes, sir.
Yeah, okay, good. And what about you, Muhammad?
Yes, sir.
Okay, good. Razan, आपने लिखा? Did you write the notes, Razan?
Yes, sir. Yes, sir.
Okay, good. Okay. Yes, Hannah, and you have to keep in mind the sign convention also. So let me also write one more question. Delta U, Hannah. Mohammed, you are right, but it will be delta U. Because
Yeah,
we
sir.
have
But
written
in the keyword there is no like delta sign, sir.
no. I know, I understand that. I know that you know it. I just want to point it out. Okay, fine. Now let us suppose if you have a gas absorbs 150 joule of heat and 150, let's keep this as 200. Of work is done by the system. calculate the change in internal energy. Okay, so I've got only answer from Muhammad, and if anyone is having any doubt or something, then you can please let me know. Okay, if you're stuck or something. How are you, Abdul Wahid? Yes, what happened? Parvati, Yusra, Razan, Minashi. Okay, okay, I'm getting the answers. Okay, okay. At the same time, all of you. Uh, okay, yes, Minashi, correct. And yes, Parvati, correct, correct. Yes, Muhammad, correct. Very good. Okay, waiting for Khalil, Razan, and I think Mazia. Achha, Yusra was here. Yusra got disconnected. Also, Abdurrahman, you have not sent me the answer. Yes. Mazia, what happened? Are you stuck or something?
No, sir.
Also, send the answer, no? Send the answer, okay? And send it to Salim, not to Learnivio. Okay, yes, Mirashi, correct. Very good. Khalil, आप कर रहे हैं?
Yes, sir. One second.
Okay, okay, okay. Okay, that is. Take a screenshot, Mehreen, and please start solving the question. Don't write the question, okay? You can look at the screen and start doing the question. Okay, Masya, this is the answer for the first one.
Yes.
Okay, fine. Do the second one. Khalil, you have not sent me the answer till now. Khalil, Abdurrahman, Abdul Wahid, Razan. Yes, Razan, are you stuck? Or are you solving it?
Sir, which formula should we use? Like, I just joined.
Hi.
So,
Did you write the notes?
yes, sir.
Okay. So what is internal energy change is equal to? Tell me, according to the whatever you have.
U
Delta.
final minus U initial.
हाँ नहीं, but उसके बारे में हमने क्या कहा था? That is that a formula?
No, sir.
That is a definition, right?
Yes, sir.
है ना? So that is not a formula. Now you tell me what is the formula? Yesterday we did that in the previous class, no? See. This thing we have written now. Okay. So Razan, see. Okay. One thing is that you should always develop an intuition for a particular problem. So if gas is absorbing 120 joule, what will happen to the what will happen to internal energy? It will increase or decrease? You tell me that.
Decrease.
It will increase or decrease? Can you please say it again?
Decrease.
Decrease. Are you saying decrease?
It's increase.
Increase. We are saying increase. So if I am giving it heat, what you are saying that it will, the internal energy will increase. Okay, and it will increase by 120 joules. Yes or no?
Yes, sir.
Now again, you tell me the same system. Okay, the same system is there, and what do I have? I am, and it is doing work, and it is doing work of 100 joule. So now you tell me what will happen to the internal energy if work is done. If you do some work, internal energy will decrease or increase?
Decrease.
Decrease, है ना? So you increased 120 and you decreased 100 joules. So what is the change in internal energy? You tell me. बताइए. आपने क्या किया? आपने 120 जूल की एनर्जी दी एंड 100 जूल की एनर्जी निकाल ली. कितना बच गया आपके पास? चेंज क्या होगा? What will be the change?
120 minus 100.
है ना? So did you need any formula?
No, sir.
No, na? So see, it's very simple. I mean, it's not actually formula. It is common sense. Delta U will be equal to whatever heat you are giving plus whatever work you're doing. Now we have to look at the sign convention, and you can see that in this case, the delta U is equal to Q plus W. Acha, okay, Khalid. No problem, no problem. Now delta U, it is equal to plus 120 because we are increasing the energy of the system, and then plus minus of 100 joules because what we are doing, we are decreasing the internal energy by doing some work, and this will be equal to 20 joules. Now Razan, you tell me. Razan, देखिए, if you get stuck like this now, please ask me, है ना? Please ask me as soon as possible. Okay, and then I will tell you whether you have to flip the notes or not flip the notes because we are short in time. Okay. So now you calculate for the next question and tell me. And Mazia, I hope you understand that it will not be minus 20, but it will be plus 20 joules. Yes or no, Mazia? क्या गलती की आपने? बताइए. Yes, Mazia.
And the negative sign. The sign.
Why? Why?
I forgot.
Okay. So please remember like this. If you are heating something, think intuitively. I think it would be very intuitive, right? Like ये खुद से आना चाहिए. Like if you are heating something, that means you are increasing the energy. And if you are doing work, then the energy is going to decrease, right? The energy is going to decrease. Calculate for the next one, Mazia and Razan, and tell me the answer fast. Yes, correct. Mazia, waiting for you. Also use your thinking, not only the formula. Yes, Maureen, correct. Razan, correct. Okay, Mazia, you know, can you please turn the mic on?
Yes.
Okay. Now, if I am heating something, then what will happen? The internal energy will increase or decrease? Tell me.
Increase.
Increase. Okay, it will increase. So what you just assume that you are the system. And what I have done, I have increased the energy. Whatever energy you have, I have increased it to 150 joules. I've increased and I have inserted 150 joules of energy, and you have been given 150 joules of energy. And how much work you are doing? Tell me. How much work you are doing, Mazia? 200 joules, na? So
Yes.
how much energy will be extracted from you? How much energy will be extracted from you, Mazia? How much? Can you please speak correctly, loudly? I can't hear you. Maybe you keep your mic near or something. Okay, 200. So how much will be left? How much will be left? I gave you 150. I gave you 150 and took out 200, na? Yes or no, Mazia?
50. Yes.
So what will be the answer?
Minus 50.
So why did you write 50? Why did you write 50, Mazia? Write another question. Mazia will tell the answer, others you don't have to tell the answer. You have to calculate the internal energy change, okay? Mazia, I'm waiting for you.
Yes, sir.
Sorry?
1 second.
Okay. Yes, correct, Mazia. Very good. Okay. Now we can move on. Now we can move on. Yes, Meenakshi, your answer is also correct. Parvati, your answer was also correct. Okay, your answer was also correct. Now we are moving towards, and we will try to see what is work and how work is done by the system. How work is done by the system, because for heating we don't have to spend much time. Yes. Okay, you don't have to send the answers now. Okay, I know you guys got it. And now we have to look inside work, okay, and how the system does work and how can we quantify that work. Okay, how can we quantify that work? So the most of the work that you will be seeing in this chapter is if you have a gas and the gas is held by some piston or something, or it is under some, there is some rigid bond, not rigid boundary but a flexible boundary, and one or two things can happen here. Either I can increase the pressure, right, and I am moving the piston down. Okay, so that means what is happening, if I am moving the piston down, I can move the piston down. And when I'm doing this, what is happening? When I'm doing this, what is happening? I am doing work on the system, because system will have some of its pressure, internal pressure of the gas, and I am opposing that force. I'm opposing that force by pushing down this piston. That means I am doing work on the system, right? So if the volume is decreased, okay, work is done by decreasing the volume. Similarly, what can happen? The gas can also do work by pushing the piston away, right? Pushing the piston away. Now here we can see that there are two things which are involved in this case. The first thing is the pressure, right? And there is a change in volume, right? There's a change in volume and there is a pressure. That means we can say that we are doing a work in which two things are involved, that is pressure and work, and hence it is known as pressure volume work. pressure, volume, work. So you must have seen this formula for work. Work is equal to what? Force into displacement, right? Yes or no?
Yes, sir.
Yes,
Is
sir.
force into displacement. Now what we are having, I mean, there is some pressure, and pressure means you have force upon area. So there is some component of force, and there is some component of distance also, because you will have volume. You will have volume. Okay. Now volume is just 3 times of distance. 3 times of distance. So let us see and derive a formula for pressure volume work. For pressure volume work. Now what I am going to take, there is I am giving some pressure. I'm giving some pressure. So this is the P external. And if P external, and this is, there will be some internal pressure, right? And when P external is equal to P internal, then nothing will happen, right? The piston will not be moving anywhere. And this is the case where we say that it is at equilibrium. It is at equilibrium. But let us say that I am pushing down the piston. So the pushing down the piston, and hence the P external is greater than P internal. Okay. P external is greater than P internal. You don't have to write. You will just listen. Now what will happen? The piston will move down. Piston moves down. So what will happen? The volume will, there will be a change in volume. Yes or no? There will be a change in volume. Tell me. Let me write it like this. Wait a second. Erase these parts. Let us suppose the piston was here, and I have moved it down till here. Okay. The piston was here, and I moved it down till here. So the piston moves L length. Yes or no? The piston move L length, but because this is a 3D piston, this is a 3D container, there will be a change in volume. There will be a change in volume. So what will be the change in volume? So as the piston moves down, the volume changes. Okay. And the volume change will be equal to volume change. It will be equal to the cross-sectional area, because if, let us suppose that if it is a cylinder, then what would happen? This length, right? This is the volume that we want to calculate, right? So if you have a volume that you want to calculate it like this, then what you can do, you can just calculate the area, the cross-sectional area times length, right? So area into length, the area of this base times length will be equal to your volume. All of you know this, yes or no? Tell me.
Yes, sir.
Yes, sir.
Yes, no? Okay, because you can see, if you calculate the area of the base, that is a square, times the length, that is a. So that will be a, that will equal to be a, that will equal to a cube. Okay, so base into length will give you the volume, will give you the volume change. So you'll have a into L. This is the volume change, yes or no? That means I can write the delta V will be equal to a times L. The delta V will be equal to a times L. And we know that the pressure is equal to force upon area. Yes or no, guys? Force upon area.
Yes, sir.
Yes, sir.
So we have got two things. We have got two things. So what we can see from here, that work, this will be equal to, work will be equal to force into displacement. Yes or no?
Yes, sir.
Yes, sir.
Yes.
Force into displacement. And what is force? Force will be equal to pressure into area,
Yes, sir.
right?
Yes, sir.
Pressure into area. And what is the displacement? The length L, correct? Yes or no?
Yes.
Now this will be equal to P times delta V. P times delta V. This will be work. Please don't write anything. Just keep listening. Okay, just keep listening. Now let us see. We have to work on the sign convention here. We have to work on the sign convention here. So delta V means the final volume. V final minus V initial, right? V final minus V initial. Now in this case, what we have to see, the work should be positive. Work should be positive, right? And work can be negative also. Work can be negative also. So work will be positive if the piston moves down, right? Piston moves down. Yes or no? Because we will have this piston, if it is moving down, that means we are doing work on the system. Yes or no, guys? Yes or no?
Yes, sir.
Right? Now, in this case, the V final and the V initial, you tell me what will be greater. If I will push the piston down, the V final will be smaller. Yes or no?
Yes.
Yes,
Ah.
sir.
So this will be equal to negative, correct? Hannah?
Yes, sir.
Right? Now, we have to make it positive, right? We have to make it positive. Now, let us see what will happen if the piston moves up. That means if the gas is doing some work, that means what will happen? The piston moves up. So in this case, we will say that V final minus V initial, it will be equal to positive, because the final volume will be larger than the initial volume. Yes or no?
Yes.
Now you can see that what is happening when I need a positive, when I need the work to have a positive value, it is giving me negative. When I want it to be negative, it is giving me positive. That means I can just write a negative sign here, and then it will be all fine. Yes or no? Then the work itself, this PV value will be negative and this PV value will be positive. But the total work that is there, it will be multiplied by the negative sign. It will make the negative positive and it will make the positive negative. Okay, so all of you understand why this work is minus P delta V. And this P
Yes.
is P external. Okay, this P will be the P external. So write this down. Let me know if you're done. Sorry. मत लिखिए. ये हम बोल देते हैं ऐसे कभी-कभी. I'm really sorry. You don't have to write this down. Please let me know if you have understood this. Yes or no?
Yes.
Yes, sir.
Yes, sir.
All of you?
Yes. Yes, sir.
Okay. Now you write a question. But you have to write a question. So our formula you can write. Please write the formula. Work is equal to minus P external delta V. Okay, minus P external delta V. Right, next. A gas absorbs 120 joules of heat and expands against the external pressure of 1.10 atm from a volume of 500 ml to 2 liters. 500 ml to 2 liters. Okay. What is the change in internal energy? Okay. So write this question. Let me know if you're done. Assalamu alaikum, Maimuna. How are you?
Walaikum salam. I'm fine.
What happened? Why are you late?
Actually, sir, I had with network issues. Then I joined at 4:48.
Okay. So you were present in the last class?
No, sir. I was absent for a week or so.
What happened? Why? Exams?
Sir, yeah, I was having my mock exams. I have from Feb 20th my final exam.
20th or 28th?
20th Feb.
20, na? From
Yes,
20
sir.
Feb 20. Okay. How was your mock chemistry? Hua?
Yeah, today was chemistry.
How was it?
Yeah, it was good.
Well done. Okay. So you have completed these chapters or all?
Yes, sir.
Achha, okay. Okay, so Maimuna, if you want some doubt classes or something, if you have completed these chapters, then you must be having some doubts. Do you have doubts from thermodynamics, equilibrium, or the other chapters?
For now, sir, I don't have because I just wrote the exam, so I'm pretty sure about the topics.
About those topics. Okay, fine. That's good. So if you have any doubts or something, you can message to Nishkar sir, and maybe we can take some time out. So maybe if you have some like around 10 doubts, then we can carve out some 1 hour. So I'm willing to give you more hours for all of those who have doubts near the examinations. Okay. So if you guys, any of you guys, if you have doubts now, then collect at least somewhat around 10 doubts, and then we can discuss that. But as an like you just take 1 month to create 10 doubts. And so in a week, you maybe try to get some 10 or 20 doubts, and then we can discuss that also. Okay. Okay, regarding this question, a gas absorbs 120 joule of heat and expands against the external pressure. Now, first thing for the internal energy question is that you have to internalize the question. How will you internalize the question? So you simply take the case, right? You simply take the case like this. What is happening? I'm heating this. If I will heat this, then obviously what will happen? The temperature will increase, and then these molecules of gases, they will be moving very fastly, and it is inevitable that this piston is going to move upwards, and then we say the gas is expanding. Now the gas expands, and we are also saying that if you are doing a work, there should be a external pressure, opposing pressure, right? You have to oppose some pressure. So if it is moving upwards, then what is going to happen? There is some P external, that is the opposing force, and that is equal to 1.10 atm. That is equal to 1.10 atm. And if it is moving upwards and it is changing from 500 ml to 2 liters, then you have to calculate the internal energy change. So first thing is that delta U is equal to Q plus W. We know the value of Q. It is given in the question. W we don't know, but for W we have the formula that is equal to minus of P external times delta V. And we know what is delta V. Yes or no? This will be what? Minus P external is minus 1.10 times delta V will be equal to 2 minus 0.5. And this will be equal to minus 1.10 times 1.5, because delta V will be V final minus V initial. So initially it was 500 ml, then it got to 2 liters. Okay. Now here the units will come into play. The units will be liter ATM. So one thing that you have to remember, that 1 liter ATM is equal to 101.3 joules. Okay, 101.3 joules. So you may take it as 100 joules also. If you are in a hurry, you may take it as 100 joules also. That means what I will write, it will be equal to minus 1.10 times 1.5 times, for liter. Rather than writing 1 liter ATM, what I will write? 101, or you can just write 100 joules. Okay. So I think this will be somewhere around 170 or something, 160, 70. That's given me, I have got some answers. 118 joules. Okay, I think
Yes, sir.
Parvati, you are giving me the last answer.
No, I forgot to convert it.
Okay. Maimuna is giving me delta U. Yeah, I think that is correct, Maimuna. Okay, fine. I think Khalil is right. It will be equal to minus of 167 joules. Right. Yes, user. I think that, I mean, around that value, you will get the answer. And hence we can write the delta U, it is equal to, we are giving 120 joules as heat plus minus 167 joules as work. So this will be equal to minus 47 joules. Okay, minus 47 joules. Please write this down. Let me know if you're done. Sorry. You have to write this down. That means questions, you have to write this down. Okay, questions you have to write down. Okay, Parvati is done. Waiting for others. Okay, is there anyone who is still writing? Is there anyone who is still writing? No? No, okay, fine. Okay. So in the last lecture, we saw that example of reversible and irreversible processes, right? Reversible and irreversible processes. So in reversible and irreversible process, you saw that we have a sandbag, right? We have a sandbag. And in this sandbag, that what we are doing, we are first of all, in irreversible process, we are pouring all the sand once and all, okay? But in the second case, what we are doing, in the second case, we are taking each grain of sand, and we are putting it in the piston, and the piston is moving down. Then we are again taking one sand particle, then we are putting it down, and we call that this is reversible. This is reversible, okay? Now you guys will tell me, in both the case, I will have to do work to put sand on the piston, yes or no? I'm going to put sand on the piston. That means I will have to do the work.
Yes.
Yes, sir.
Yes.
Yes. Okay, fine. So what do you think? In both the cases, will the work that I will be doing will be same or it will be different?
It will be different, sir.
Different, right? Now you tell me which will be more easy for me, the irreversible one or the reversible one?
Irreversible.
Irreversible one, right? We can easily take the sand and we can pour it down all at once. But in the reversible process, I will have to take one sand particle, and it is going to take a lot of time, and as well as time, it is also going to take a lot of work from me. So one thing is clear, that reversible work is going to be different than irreversible work. That means we have to derive some formula in the case of reversible work. So please, what we are going to now derive is the reversible work. Okay, so you please just look here. Don't have to write this down. Reversible work. First of all, we will say that if I am putting one sand particle, that means there will be a slight decrease in the volume, and there will be slight movement in the piston, and let us say that slight movement is equal to dl. So displacement of piston will be equal to dl, okay? And that means the change in volume we will take as dv for each step. This will be equal to the area times dl, because dl is the movement of the piston. Is there any doubt till here, guys? Tell me. Is there any doubt till here? No, na?
No, sir.
No. Okay. Now, similarly, what I can say, we can write these things, that the pressure will be equal to force upon area, and that will mean the force, it is equal to pressure into area. And then we can write the small work that I am doing in each step. It will be equal to force time displacement dl, and here force is equal to P into A into dl. So rather than again, we will again have minus P external. I hope you understand why the minus sign is there, because we are having work because of the change in volume that we are writing about change in volume. That is why we have to give a minus sign here. We have explained this in the previous example. Now, rather than delta V, we will have del V. That means a small change in the volume, right? A small change in the volume. I hope there is no problem till here, guys. It is very similar, but here we had, this is for irreversible work where you are just looking at the final and the initial conditions. In this case, we are going to integrate the system. We are going to integrate in order to calculate the total work. Okay, to calculate total work, integrate both sides. We are going to integrate both sides. Now, when we are going to integrate on both sides, what will happen? We will have dw. This will be equal to integration of minus p external delta v, minus p external delta v. So the p external, since it is a constant, is not going to change, right? It is not going to change. What we can write is that this, fine. One thing I can write, that this integration sign and this delta sign, what it will do, I am not going to explain it. You can just eliminate integration and differentiation, right? Okay, how many of you have seen integration and differentiation before this?
I have seen, sir.
You have seen. Do you guys understand integration?
Yeah,
Differentiation?
yeah, I have studied it. Yeah.
अच्छा, math है आपके पास?
Yeah, there is math, but they are not teaching in math, but I studied it from YouTube. So yeah.
Okay, fine. In the integration, so you won't have that in math, but you will have that integration in 12th, I think. Yeah.
Yeah,
But in
sir.
physics,
12th.
physics you must have used na integration, guys.
Yes,
Yes, sir.
Yeah, sir. In
Yes,
physics
sir.
is there.
Yes, sir.
Yes, sir.
Physics you must have used, right? So I hope if you have heard integration, that means you would have heard it as the opposite of differentiation. So what I'm going to do, I'm just going to cancel this. This is not right. This is not right to cancel integration with differentiation. But the result is what you want, what you are getting. The result is correct. Now I will call this work as reversible work by writing the subscript WREV. And I will take this P external away from the integration sign. And I will just integrate the del V. I will just integrate the del V. Now, when I'm going to integrate this del V, it is going from V, that is initial, to V final, right? It is going from V initial to V final, right? And when we have just del V, what is going to happen here? It is going to get minus Px external. Now, integration of del V will give me V from V initial to V final, right? V initial to V final. Next, what we are going to do? Next, we are going to write that this P external is equal to V final minus V initial. Okay, and this will be equal to V reversible. Oh, sorry, W reversible is equal to minus of P external times delta V times delta V. Now this is completely same as you have seen in the irreversible case. But for this, what we can write, we can also write this in terms of, which is more important, in terms of P internal. So we can only write the reversible work that is done in terms of P internal. So we know that P external, this will be equal to what? See what was happening? At this point of time, when I have not added any sand, then I can say that P external and P internal both are equal. Yes or no? Then only the piston will not move. Yes or no, guys?
Yes, sir.
Yes.
Yes, sir.
Now what I am doing? I am increasing. I am putting one particle of sand. When I am putting one particle of sand, I will increase the pressure by a very small amount. So initially P external was equal to P internal, right? I can write P external is equal to P internal, plus I will write dP. This will be the P external. Now when I have added one grain of salt, one particle of salt, it will be equal to P internal plus dP. dP is the small pressure that is added when I add one particle of sand. Then we can write, I'm going to start from here, this part, and I will be writing here the integration of dW, small work, will be equal to integration of minus of P external dV, minus of P external dV. Now I can write this as, again, this is work reversible. this will be equal to what? Minus, I can take it outside. Integration of P external is equal to P internal plus dP. Yes or no, guys? P internal plus dP
Yes, sir.
times
Yes,
dV
sir.
times dV, and this will be equal to minus of. Now I can write this as integration of, first of all, we have P internal into dV plus, I can also write integration of dP times dV. Yes or no? Any problem till here, guys?
No, sir.
No problem till here. Okay, fine. This practice, no use. Okay. Now, as you know, this dP and dV, dP and dV both are very small, right? Very small, very small. And if you multiply two things which are very small, then I can say that if I compare dP into dV integration, it will not be very, very small than this part, that is P internal into dV. That is why what I'm going to do, I'm going to neglect this because it is going to be very small. This is going to be very small. Okay. Hence we are neglecting this. Because dP into dV, it is going to be very small. And further I can write that this P internal, this will be equal to work reversible will be equal to minus of integration of P internal times dV. Okay. Now, when I am talking about this P internal, that is the internal pressure of the system, right? And this volume is also of the system. This volume is also of the system. Now we know that from ideal gas equation, I can represent this P internal, that is the internal pressure of the gas, in terms of also its volume. So I know that PV is equal to nRT, and hence pressure will be equal to nRT upon V, where everything else is common, but only what is changing, the volume will be changing. I can write this pressure as minus of integration of nRT upon V times del V, right? Times dV. Now this will be equal to, now since nRT are common, minus of nRT integration of 1 upon V dV. And integration of 1 upon V, it is equal to what? Tell me, guys, it is equal to ln. Yes or
Log
no?
of something, sir.
Log of V. Okay, it will be equal to natural log of V. Here you have minus nRT, and then you have ln of V, V1 to V2, and yeah, V initial to V final. You can write it in the integration form also. And then you can further write it as minus of nRT ln. First we will write V2, and then we'll write minus V1 ln V2 minus of ln V1. Now we can write this as minus of nRT now there is one ratio formula, the quotient rule, which says that log of A, ln of A minus ln of B is equal to ln of A upon B. So we can write this as ln of V2 upon V1, ln of V2 upon V1. So this is the V reversible. So we have got V reversible is equal to minus of nRT ln V2 upon V1. So ln, it is equal to log of base E, and if I want to write log of base 10, because we operate mostly in terms of log of base 10, so this is equal to 2.303 of, I can write log of E as 2.303 into log of base 10. So I will replace this ln and I will write this is equal to 2.303 minus nRT log of V2 upon V1. Okay, V2 upon V1. Okay, and also since you can write, since P1 V1 is equal to P2 V2, we can also write what we can write V2 upon V1 V2 upon V1, it is equal to P1 upon P2 because pressure and volume are inversely proportional. So work reversible will be equal to minus 2.303 nRT log of P1 upon P2, log of P1 upon P2. Okay, so we have done a long derivation here. So what you need to do is, you please write this derivation right now, okay? That will be better. So write this down for reversible work. And slowly write it down. If you have any doubt, we can spend some time here, okay? Then when we will also do some questions now. While doing the questions, will be clear.
So, sir, so this all these equations are for reversible work.
Yeah, reversible
So
work.
what about irreversible work?
Yeah, that is it. This is here now. Irreversible work.
So this
Initial
one
and
only.
final. Just this one. Because we just need the initial and final, nothing else. Okay.
Yes. Okay.
Can you slow down?
Yeah, sure. I think I can scroll till here at least. PI means P internal, okay? P internal. Should I scroll down? Done, guys?
Yes, sir.
Let me know, okay, if you're done. We have right till here. Raise your hand if you're done, okay? Okay, a bit up. Okay, fine. Let me know if I have to move a bit more up, okay, Abdurrahman? Okay, most of you are done. Waiting for Abdurrahman, Abdul Wahid, Mahreen, Minashi, Razan, Khalil. Keep your hand raised, okay, if you're done. Okay, Muhammad is also done. Razan is done. Okay, waiting for Abdurrahman, Abdul Wahid. Yes, Abdurrahman. Okay. Now, you all can lower your hands, okay? Please lower your hands. Let us see a few cases, okay? Let us see a few cases. And what we are doing, we are heating a particular body. We are heating a particular body and different types of system, okay? Different types of system. So let us say that what is happening here. You have a closed vessel, and initially the temperature was, let us say, 50 degrees Celsius of the system, 50 degrees Celsius. And what did we do? We applied heat. We applied heat. Okay, so this was the T initial, 50 degree. So what can you tell me about T final? This is a closed system, okay? This is a closed system, and we are heating it. We are heating this. So what can you say about the T final? It will be greater than 50. T final will be less than 50, or T final will be equal to 50. Tell me, guys, A, B, or C?
A.
A. I hope all of you agree. Yes or no? A?
Yes, sir.
Yes. Okay, fine. Now let us see. Let us see. If I have a system like this and there is a movable piston, there is a movable piston like this, okay? And then what we are doing, we are heating the system. Then we are heating the system. The T initial here also, it is equal to 50 degrees Celsius. Okay, it is also equal to 50 degrees Celsius, and we are heating the system. So what can happen if I will heat the system? Then the piston will move up. Yes or no? Tell me.
Yes, sir.
Yes, sir.
The piston will move up. The piston will move up. So now please see what is happening. If it is moving up, acha. So if I start heating, the pressure will increase, right? The pressure will increase. Pressure increases, right? Pressure increase. That means the movement of the particles inside this particular molecule will also increase. The temperature also increases, right? But if the pressure increases, the piston moves up. So piston is up. And if piston is moving up, that leads to the volume is increasing. Yes or no? The volume will increase, correct?
Yes, sir.
Yes, sir.
If the volume will increase, then again the pressure will go down.
Yes.
Yes or no? And then again the temperature will go down. Yes or no? If
Yes.
the pressure
Yes,
goes
sir.
down, है ना? That means we are having the internal pressure, the molecules which are moving, they will be moving a bit slowly now. And the kinetic energy is only directly dependent to the temperature. The temperature is determined by the kinetic energy. Kinetic energy means how fast the molecules are moving. They determine the temperature of a particular gas. Kinetic theory of gases in the chapter states of matter. Now, as you can see, if I say that I heated something, and there was a change in volume, so much so that the T initial was equal to T final. The T initial was equal to T final. That means I can say all the heat was used for change in volume. Yes or no?
Yes, sir.
That is for work, right? Because if you are heating something, what is going to happen? The temperature will increase. But if we increase the temperature and then we also increase the volume, then temperature is going to go down. If the temperature is going down, that means what you're doing, your work. That means there is a whatever heat you are giving, that is being converted into work rather than into temperature. It is converted into work rather than temperature. And if the T initial is equal to T final, that means I can say that delta T is equal to 0. Yes or no?
Yes, sir.
Yes or no? And then this is what isothermal process, correct?
Yes.
Yes,
Yes.
this is isothermal process. So in this case, I can say that in isothermal process, what happens? Tell me. In isothermal process, whatever the change in internal energy, it will be equal to 0 because we are giving in heat, Q amount of heat, right? So plus Q and all the heat, that means Q amount of heat, whatever we have given, this will be some joules, some X joules, and the same amount of work is also done because that means in isothermal process, Q it is equal to W, Q it is equal to W, right? Q it is equal to W, and delta U it is equal to what? Q plus W, but since we are giving heat, so Q will be plus Q. The magnitudes are same. That means I can write Q plus minus Q. Why? Because this W now, this W, it is equal to the minus of Q. That means we are giving out that much amount of energy in terms of work done. In terms of work done. I hope you can write this down. Yes or no? Tell me, guys.
Yes.
Right, the heat, it was used for the change in volume, that is for work. So whatever plus Q we are giving, that is being taken out as minus W. That is taken out as minus W, and hence we can say that in isothermal process, delta U, it is equal to 0. The change in internal energy, it is equal to 0. Whatever amount of energy I was giving in as form of heat, what it is happening, it is taken away by the system in terms of work done. So system is doing work and spending all that energy that I gave it in. And hence delta U, it is equal to 0. Delta U is equal to 0. And also what we can write here is, if delta U is equal to 0, that means the Q plus W, it is equal to 0, and hence I can say that Q, it is equal to minus W, or we can also write W, it is equal to minus of Q, right? W is equal to minus of Q. Now from this, what we will do, we will write a question. 2 liter of an ideal gas, 2 liter of an ideal gas at a pressure of 10 atm expand isothermally, expands isothermally at external pressure of 1 atm. So 10 atm is the pressure inside the gas. Okay, 1 atm is the external pressure. Please remember this. And we have also used the word isothermally at external pressure of 1 atm. How much heat is absorbed? How much heat is absorbed? And how much work is done? And how much work is done? Write this question with me, okay? How much work is done if the gas expands to 2 liter, if the gas expands to 2 liter. First of all, we will solve this question, then we will calculate the answer. First of all, you have to solve this question, okay? So you have to see what steps you are going to take. And so first of all, what is happening in this particular system? What is happening in this particular system is that there is a 2 liter of ideal gas at a pressure of 10 atm expand isothermally at external pressure of 1 atm. How much heat is absorbed? So that means obviously we are heating the system, and it is the case of isothermal process, right? So the piston is going to move up. And then what is happening? The piston is going to move up, and that means there is some work done. There will be some work done, right? And it is what? Isothermal. The first thing is that whatever work is done, it is equal to the minus of Q, right? It is equal to the minus of Q. So this means that the magnitude of work done is equal to the magnitude of heat given. But since work is done by the system, we are taking it as minus sign. We're taking that as minus sign. So work is equal to Q, but there is a negative sign. Why? Because what we are doing here, we are work is done by the system. The system is doing the work. Okay. And also we can write delta U, it is equal to 0 because it is an isothermal process. It is an isothermal process. Now you have to calculate, you have been given expands to 10 liter, not 2 liters, sorry. 10 liters, okay. So we have the volume, initial and final. We also have the external pressure. So we can write W, it is equal to minus of P external into delta V. Now tell me guys, what is the P external?
So do we need to
external?
calculate like the change in pressure?
Change in pressure, what do you mean?
Like there are two pressures, right?
So what is this? First is 2 liter of ideal gas at a pressure of 10 atm. That means it is the internal pressure. There will be always two pressure. Okay. So see, inside here it is P external is equal to 1 atm, and P internal it is equal to how much? 10 atms, and then obviously it is going up, so it is expanding. Yes or no? Whenever you will have an expansion or compression, it is expanding, na? Who asked this question? Can you speak at least now?
Yes, sir.
Yes, Mohammed. You understood that why there are two pressure?
Yeah.
Okay, one is internal and one is external. So this 10 atm is the internal pressure. We have to write here the P external. So P external it is equal to 1 atm. So 1 atm delta V is 10 minus 8 liters, right? 10 minus 8 liters, and this will be equal to minus of 8.
So 10 minus 2
Liter eight.
liters.
Sorry, 10 minus 2 liters, which will be equal to 8 liters atm, 8 liter atm, and this will be equal to minus of 8 into 100 joules, will be equal to minus of 800 joules. Yes or no?
Yes, sir.
This is again, this is an approximation of liter atm, which is actually it is equal to 101.3 joules. Okay, so if you write 101.3, that means it will be somewhere around 810, I guess. Yeah, approximately 809 or 10. Okay, if you write 101. So this is the work minus of 800 joules, and we have written work, it is equal to minus of q, right? And hence q will be equal to minus of w, which will be equal to minus of minus 800, which will be equal to 800 joules. Okay, 800 joules. But rather than all these equations and numbers, now what I want is that you have to internalize this idea that if you're heating something, then heat is given on the system, and then the work is done by the system. Then work is done by the system. So heat, this will be always in positive, and whatever value of this heat is, the same value of the work will be there, but in the negative sign. And you can see this very clearly. You have 800 joule as the work, minus 800 joule as the work, and the heat is 800 joules in positive sign. That means you're giving heat to the system, and the heat is used by the system to do work. Heat is used by the system to do work. So you can write this down. So in the questions of thermodynamics, the words are very important. In this question, isothermally was the word that was very important. And only due to isothermal process, we can write delta U is equal to 0. And hence we can find out both the things, the work done and also the heat. Okay. So you have to keep in mind these words. I will write the next question. All the things are same, but we are changing the values are same, but we are changing the conditions. Okay. We are changing the conditions. So write this down. Raise your hand if you're done. Then we can write the next question. Okay, Minashi is done. Okay, so I think most of the people are done. Okay, fine. Okay, I think most of you are done. So write the next question. Boliye.
Questions like these, if we write 800 instead of 810, so the teacher won't put the marks, right?
I mean, it depends on the teacher actually. Okay, so what I would say is that you write this as W, it is approximately equal to 800 joules. Okay, initially when you have solved it, and after that, if you get time now, so please see how the question, you have to judge the question paper. So this is a matter of time, because I know that you know multiplication. So you can do write 810 if you multiply, but it is a matter of time. So you have to judge the question paper. So if the question paper you think that it is very lengthy, then you will rather write 800 joules. And if the time permits later on, then you will correct it to 810 joules after multiplication. So obviously, it is always better to write the accurate answer. Hai. So you have to judge, Yusra. Okay, fine. If you have time, and it is multiplication. So I know that, I mean, it is not, we are not approximating, we are saving time, and we are not approximating here. So if the paper is lengthy, you write 800 joules and just wish that the teacher will give you some marks, or maybe she will cut half marks or something. Anna,
Okay, sir.
how is your teacher? But is she lenient, or I mean, is he or she lenient?
She's lenient. She's kind.
She is lenient. Okay, fine. So then you can hope for marks. So these things they mainly depend on the teacher. Okay. Now write the next question. All the values are same, but we are changing the conditions, right? How much heat is absorbed and how much heat is absorbed and how much work is done if the gas expands to vacuum. If the gas expands to vacuum. Okay. Now in this case, what have we changed? You see that. Okay. And what is the word that you think it is crucial? What word is crucial in this particular question? So the values are of same, that is of the previous question. This is an extension in which we have changed the condition. So write this and then tell me, first of all, what do you think is different here from the previous question?
So 0.
What is 0? Why 0?
Work done, sir, because no
And-
external pressure.
And well, I asked you something else. What is different here?
It's in vacuum.
It's in vacuum. What happens in vacuum?
I think external pressure will be low. I mean 0.
You think.
No, I'm sure.
Okay, fine. So all of you, can you see that vacuum is the word that you have to look? Okay. So you, whenever you are doing some questions and you see that words are important, okay? These words are important. Mainly whenever you have numericals, you are following the numbers, but in this case, words are important. So whenever you have vacuum, you can imagine vacuum, like if you are in space, there is no pressure, right? There is no pressure. So at vacuum, in vacuum, P external, it is equal to 0. P external, it is equal to 0. And see what is happening. Now you have to also figure this out qualitatively, that if you have a piston like this, right? If you have a piston like this, now that means if you are vacuum, that means there is no external pressure, there is no piston, right? So the gas is just moving away. So gas is not doing any work, because if it is moving in a particular direction without opposing any force, right? Where you have to oppose a force in order to do work. You have to oppose some force. Now, if there is no force available, that means it is not doing any work, right? It is not doing any work. So in vacuum, P external, it is equal to 0, and therefore the work done, it is equal to, you can write this in the terms of formula, but in this case, you don't even need these things, because the work will be equal to 0 into delta V, which will be equal to 0. And since W, it is equal to minus of Q, Q will be also equal to 0. And the delta U, it is also equal to 0. Delta U also will be equal to 0. Okay. So write this down. I hope all of you understood this. Yes or no?
Yes.
Right. Okay. And this is the only, this case is only when you have isothermal expansion. Okay. Isothermal expansion. Okay, write this down. Let me know if you're done. Because we have kept that as isothermal expansion. Also, those who have written this till here, you can write one more point. expansion of gas at P external, it is equal to 0, is also called as P expansion. It is also called as pre-expansion. Okay. Work done in free expansion is always 0. So I think I don't have to send today's PDF because I hope you're writing most of the parts. Write this down. Let me know if you're done. Done, guys? Okay, I think most of you are done. Write the third part of the same question. You have to calculate the same thing, how much heat is absorbed. How much heat is absorbed and how much work is done if the gas expands, if the expansion takes place. Expansion takes place reversibly. Okay, reversibly. So in this case, you all know that again, it is isothermal process, and hence delta U will be equal to always 0 because it is isothermal process. And you will have Q, this will be equal to minus W, and here in this case reversible, and here in this case it will be reversible. Okay, and we know that work reversible, it is equal to, so I'm putting this minus sign, and then again bracket here I will be writing the work reversible. Work reversible, it is equal to minus of 2.303 nRT, right? 2.303 nRT log of V2 upon V1. V2 upon V1. Now I can see that this minus and minus will cancel each other. It will become 2.303. And rather than writing nRT, what we can write it this as PV, because we don't have number of moles and all. Okay, so we can write PV. So this will be nRT into PV log V2 upon V1, log V2 upon V1. So in this case, you will be writing the internal pressure, right? What is the internal pressure starting in 2.303 into 10 atm into what is the volume? Initially, the volume is 2 liters, right? And log of V2 upon V1. What is V2? V2 in this case is 10, right? 10 by 2. This will be log of 5, and this will be equal to 2.303 into 20 into log of 5 liter atm. Log of 5. Okay. Now I'm not teaching you log right now because in this chapter you will not be needing much of log. You will be needing log in the chapter equilibrium. Okay, there at that time I will be teaching you log. For at this point of time, you can just write log 5, which is equal to 0.70. 0.70 into, you can write 100 joules. Okay, 1 liter atm, it is equal to, I'm just writing 100 joules. So now you can calculate this and tell me the answer in chat. Okay, and this is equal to what? This is equal to the Q. and a Q it is equal to minus of V reversible, and we have got the minus of V reversible. So we are exactly calculating the Q, and the work done will be the negative of that Q. It will be the negative of that Q. So this is 2.303 into 7 2s are 14. I think it will be 140 joules. Oh, 70 20 na? It is 70, yeah, and 20, it will be 1400. So I think it will be 3224, which will be equal to, you can write this as 3.22 into 10 to the power 3 joules, which will be equal to 3.22 kilojoules. So write this down, let me know if you're done. This is what? This is the Q. And we know that Q, it is equal to 3.22 kilojoule. W, it will be equal to minus of 3.22 kilojoules. So write this down, let me know if you're done.
Sir, can you scroll up?
Yeah, sure. Is this much fine?
Sir, I have a doubt, sir.
Boliye.
So in the second line, sir, like the place where PV, you took
PV.
V as the initial volume, sir. So should we take initial volume or final volume?
Initial volume.
Okay, sir.
Okay. Because I mean, because the initial volume is given to us, if final volume was given, you can also take the both of, if the pressure you are taking as initial pressure, then you have to take the initial volume. Okay, so I hope you understand. If I have a gas, right, and at this point of time, the pressure it is equal to 10 atm, and the volume it is equal to 2 liters, and they are saying that it is going to expand, right? It is going to expand. So what is going to happen? The volume will increase, right? And if the volume will increase, the pressure will decrease. So we have the final volume, but we don't have the final pressure. That is why I have taken that as the initial pressure and initial volume. Okay. The nRT is going to be same only. Pressure and volume, they will complement each other. If one is increasing, the other will decrease. Done, guys, all of you?
Yes.
Yes, sir.
Okay, fine. So what we have learned till now, we have learned that delta U, it is equal to Q plus W, right? Q plus W. And we have also learned and we have also read one more formula, that delta U, it is equal to Q plus, now since W, it is equal to minus of P external times delta V, right? Times delta V. Now we have learned that there can be some processes that we can make use of, and then we can generalize these parts. So if you have isothermal expansion, what is going to happen in isothermal expansion? The temperature, that means the temperature is going to be constant, right? And in this case, all the work done, it is all the heat given to the system is converted to work done by the system, and that is why the delta U it is equal to 0, and Q it is equal to the minus of work that is done, the minus of work that is done. Another case can be if you have an isochoric process. Isochoric. So in isochoric process, the delta V will be equal to, the volume change will be equal to 0. See, if the volume change is equal to 0, the work done will also become equal to 0. And in this case, we can say that the delta U will be equal to only the heat given to the system, and I'm writing QV in order to say that this is the case in which the volume is constant, in which the volume is going to be constant. Okay, so heat will be equal to the change in internal energy when the volume is constant. Then we have looked at one more case in which we have free expansion. Okay, so in free expansion, the P external, it is equal to 0. P external, it is equal to 0. And hence, in this case also, the delta U, it will become only equal to the heat given to the system. Now we will write one more part, but for that, we have to first of all understand what is going to happen. We have taken the case of isothermal, isochoric, and there is a free expansion that is happening. We can also take a case in which the pressure is constant, okay? Because we chemists, when we work under the atmospheric pressure. So whatever reactions that we do now, always what is there? The pressure is always constant. In most of the cases, 90% of the reactions that we do it at the external pressure of 1 atm, that is the atmospheric pressure. So we need to niche this down, and we need to narrow it down, and we need to make a case in which the external pressure it is equal to 1 atm, and then we will start our story, that is the chemist story. Till here we were just learning the basic of thermodynamics, that is generalized thermodynamics. Now we are going to narrow it down towards the chemist thermodynamics because of this one criteria. Whenever we are doing experiments, it is done inside the external pressure of 1 atm. So please tell me if you have written this down, let me know, because these things you have to write it down. So I think I don't have to share much today, but I will look into it. Done, guys?
No, sir.
No, okay. You can raise your hand if you're done. Okay, I think I can move down now. Now, let us try to write everything in terms of at constant pressure. So write delta U. No, so just listen to this. Don't write this. Delta U, this will be equal to QP. And why am I writing QP? QP means whatever we are doing, it is done inside a constant pressure. It is done inside a constant pressure. Plus minus of P external into delta V. P external into delta V. And since this P external, it is what? It is a constant. We can just write this delta U as U2 minus U1. It is equal to the heat involved in a particular, the heat involved plus P of, I can write V2 minus V1. P of V2 minus V1. And what I will do, I will just place this QP this side, and I will bring this, sorry, what I will do, I will bring this particular P V2 minus V1 in this side. So I will write QP. It is equal to U2 minus U1. Okay, U2 minus U1. This plus it will become minus of P of V2 minus V1. Okay, now I can write this as U2 minus U1 minus of PV2 minus PV1 Now, when I'm opening the brackets, U2 minus U1, this minus PV2, and this will become plus PV1. And whatever the heat is involved at constant pressure, it will be equal to U2, U2, and we have minus of PV2, and here we have plus of PV1, since we have sent it here. So we can write this as U2 minus of PV2, and then this will be, so U2 is minus now. U2 is minus. I need to do this. Wait a second. This is fine. Minus PV2 plus PV1. The U2 that is having a positive sign, and then we have V2 minus V1, V2 minus V1. Okay, fine. U2 minus of PV2 minus of U1 plus of PV1. Okay, plus of PV1. There should be one thing which should be having U2 minus V1. PV2 minus V1. And U2 minus V1 is equal to PV2 minus PV1. Oh, I made a mistake, guys. Wait a second. I made a mistake. I forgot this minus sign from here. I forgot this minus sign from here. So let me redo this thing again. Wait a second. So let me first of all write this as U2 minus U1 is equal to QP minus of P external V2 minus V1. Now this will be all fine. And then I can write QP, it will be equal to U2 minus U1 plus of P external, that is PV2 minus PV1. PV2 minus P of V1. Okay, PV2 minus PV1. I will write QP equal to U2 minus U1 plus of PV2 minus PV1. Now I will just rearrange this term, U2 plus PV2. Then I will write plus, up to minus of U1 and minus of PV1. This will be equal to U2 plus PV2. I will take both of these minus as common, and then this will be equal to U1 plus PV1. U1 plus PV1. Okay. Now this is what this quantity, internal energy plus the product of pressure volume. Internal energy plus the pressure plus the product of pressure volume. Both of these will be having energy terms, and we will introduce a new term for this because this is the heat involved. This is the heat involved in constant pressure, and then we have given this a sign of H. So this will be H2 minus, and this will be H1, which will be equal to QP, and we will write that QP, it is equal to delta H. Now that means we have given a different name for the energy or heat involved. Heat involved at constant pressure is called as enthalpy. Okay, it is called as enthalpy, right? So the enthalpy, if somebody asks you, or if you have, what is enthalpy? Enthalpy is just the heat involved at constant pressure, and heat involved at constant pressure. And if I want to talk about its definition, it is what? It is the sum of internal energy and the product of pressure volume Okay, so whatever heat is involved at constant pressure, that is equal to enthalpy. So in this case, we can write if P external is equal to constant, then the QP, it is equal to delta H. Okay, QP, it is equal to delta H. So please remember these two things. At constant volume, it is equal to delta U, and at constant pressure, it is equal to delta H. Okay, this will be important for you guys when we are talking about the heat involved at constant volume and heat involved at constant pressure. So enthalpy is nothing, it is just the heat involved at constant pressure. Heat involved at constant pressure. Then you can also write, since, no, not right, but you can just see H is equal to the internal energy plus PV, right? Now all of these terms are what? A state function. H is equal to this much, and U, comma, pressure and volume all are state function. Hence, enthalpy is also a state function. Hence, enthalpy will also be a state function. Okay. Right. Next thing is that the relation between delta H and delta U. Delta H and delta U. So we know that delta H, it is equal to, you can write HA, sorry, let me write HB minus HA. Let us say there is a reaction in which A is converting itself to B, right? So final minus initial. Internal energy will be equal to final minus initial, right? So now you will tell me HB, it will be equal to UB plus, the pressure is constant, so P, and there will be VB, right? And then we have HA. This will be equal to what? Tell me, guys. UA plus
PVB. I mean PVA.
PV, right? Not PVB, PVA. Now we can write delta H is equal to, delta H will be equal to UB plus PVB minus UA plus PVA. And what else we can write? We can rearrange this and we can write that UB minus UA, okay, UB minus UA plus PVB minus PVA. Just look at this now, if it makes sense to you. You can see this, UB is positive. Now PVB is also positive. You can see that UA was negative here, it is also negative here. PVA was negative because minus into positive negative, and it is also negative here, right? So you can see that all of these are fine. We have just rearranged this, yes or no? Any problem here? No, no?
No, sir.
No. Okay. Now you can write this as
No, sir.
delta U plus, we can take P as common, VB minus VA. This will be equal to delta U plus P delta V, right? This is equal to delta H. Delta H is equal to delta U plus P delta V. Delta H is equal to delta U plus P delta V. And since we know, since PV will be equal to what? nRT. PV will be equal to nRT. So we can further expand this down, and we can say that P of VA will be equal to number of moles of A, and then RT because only the number of moles is going to change if I go from A to B in a particular reaction, right? The volume and the volume is obviously it is going to change, and that is why we have from nRT that is only going to change. What is going to change? The number of moles if the volume is changing. We can also write PVB is equal to number of moles of B times R times T times R times T, and hence we can write P VB minus PVA, that is equal to NBRT minus NART. Yes or no, guys? And then we can take RT as common, and this will be equal to NB minus NA times RT. We have taken NB and NA this side and RT as common. So we can say that this P delta V is equal to NB minus NA into RT, and hence P delta V, it is equal to number of moles. And since we have taken the ideal gas equation, the change in the number of moles of gas times RT. And therefore, we can write delta H as delta H. This will be equal to the delta U plus delta NG RT plus delta NG RT. Now let us write all of these things. What do they mean? Delta H, it is the energy exchange or energy change at constant pressure, right? The delta U is what? The energy change at constant volume. Right? Whatever heat is involved at constant volume, that is what? Delta U. And what is delta NG? Delta NG, this is equal to plus delta NG is change in number of moles of gas times R times T. Okay, times R times T. Okay, now we will use this particular equation. Okay, we'll use this particular equation to solve a problem. So all of you understood this particular derivation, yes or no? We have derived the relationship between the delta H and delta U, delta H and delta U. So this equation is very important, and this will be used in solving many questions. Okay, delta H is equal to delta U plus delta NG RT plus delta NG RT. Now we can write reaction of, please write this with me, reaction of cyanamide NH2CN solid with oxygen gas gives out heat at constant volume, which was measured to be minus 742.7 kilojoule per mole at 298 Kelvin. Calculate the enthalpy change for this reaction. Okay, calculate the enthalpy change for this reaction. The reaction is given as NH2CN solid plus 3/2 moles of O2 gas. It is giving me N2 gas plus CO2 gas plus H2O liquid. Why H2O liquid? Because at 298 water is in liquid state. So write this question. Let me know if you're done. And after writing this question, you have to tell me what are the important words in this particular question. Okay, the words which are important in this question. So please write this down. हाँ बोलिए.
Delta U is equal to delta H.
Delta U is equal to delta H. Muhammad. Yes.
Sir.
What are you saying? Delta U is equal to
Delta H.
Why are you saying that? I don't understand. I mean, what do you mean? Yes, Mohammed, can you elaborate on that?
Oh, sorry, sir. I thought delta H equals to heat at constant volume.
No, na. Okay, all of you have written this question, yes or no? Write this question and then tell me what are the important words in this particular question. You have to look at the question and tell me some words which are important, and that will help me in answering this question. Most of the things that you will be dealing now here, it will be always in terms of energy. Okay, and you have to now look and identify what energy is this. Is this delta H? Is this delta U? Yes, Parvati, correct. Very good. Yes, Yusra, correct. Yes, Mazia, correct. See, this is important, na? That you identify what is the important word. The important word is here constant volume. Constant volume. Yes, correct, Minashi. Minashi, one more thing that I will say is that try to identify inside you don't infer anything, you just see what is important in the question. So delta V was not given. So I would have appreciated if you have said constant volume, but still your answer is right. Delta V is equal to 0, that means constant volume. And what happens at constant volume? Whatever heat is given out, whatever energy is involved at constant volume, it is equal to what? Delta U. So from this question, we can say that delta U, it is equal to minus 742.7 kilojoule per mole. Yes or no? Right, guys? Yes or no?
Yes, sir.
And
Yes.
what is delta H? They have asked to calculate delta H, which will be equal to delta U plus delta NGRT. Delta NGRT. Okay. So we have got delta U. What will be delta NG? So number of moles of gas in product minus number of moles of gas in reactant. Yes, guys, tell me how many moles of gas are there in product? How many moles of gas? How will you look? You have to look at stoichiometry. Okay. Don't go to the initial concentration, whatever that they have given. It's not required. You just have to look at a particular equation, chemical equation, and tell me according to stoichiometry. So according to stoichiometry, 1 mole of nitrogen, 1 mole of CO2. So in this case, you have to first of all read this particular equation. How will you read this? You will read this as 1 mole of NH2CN solid plus 3/2 moles of O2 gas is giving me 1 mole of N2 gas plus 1 mole of CO2 gas and 1 mole of water liquid. Okay, so in this case, we can see that the product has 2 moles of gases minus number of moles of gas in reactant is 3/2, that is equal to 1.5. Yes or no? So this will be equal
Yes,
to
sir.
0.5 mole, or this will be equal to half mole. Okay, half mole. Now you have all the things, and you can find the delta H, which will be equal to delta U, that is minus 742.7 kilojoule per mole. Okay, now you have to write this in terms of standard units. So you will write into 10 to the power of 3 joules per mole plus 1/2 into R will be 8.314 kilojoules per Kelvin per mole. Kilojoule per Kelvin per mole into 298, that is the temperature. So you have all the terms here, and you can just calculate the answer now. Okay, Maimuna has calculated delta H is equal to, okay, fine. Yes, Maimuna, that is correct. I think approximately, I think that is correct. Okay. So you will get the answer approximately equal to minus 741 kilojoule per mole. Okay. You calculate this. Write this down. Let me know if you're done. Okay, writing this.